Hi everybody, Mrs. Danielson here, and today we're going to talk about finding the polar form of complex numbers. Let's go ahead and take a look at my iPad, and we're just going to get going today. We're going to start off by just talking about what a complex number is. We talked about that in our last video. Remember, a complex number is a form that's a plus bi, where a is a real number and b is our imaginary number, and we can plot those on a coordinate grid if we put on the x-axis our real number and on our y-axis our imaginary number. Okay, so if we were to plot a plus bi on this rectangular coordinate grid, right, a would be down here on the x-axis and b would be up here on the imaginary axis, like that. And let's say I plot right here our number x, z equals a plus bi. All right, so we worked on that in the last video, just plotting those numbers and adding and subtracting numbers that are complex form. Okay, so today we're going to say, all right, if I draw a vector like that going from the origin up to our complex number, okay, then this vector right here has a length called r, and r is called the modulus. Okay, and then there's also an angle going from the x-axis up to our modulus, and that angle is called the argument. And if we want to write this complex number in polar form, then we need to be able to find the modulus and the argument. We need to be able to solve for both of those things first. Okay, so first let's talk about finding the modulus. If I was to look at this picture I've drawn and then think of this as a right triangle like this, then the length on that vertical side would be b, and the length on the horizontal side would be a. So if I think of that as a right triangle and I want to solve for the hypotenuse, then I could use the Pythagorean theorem to do that, right? That would be r squared equals a squared plus b squared. Okay, and then you just take the square root of that and you would get the square root of a squared plus b squared. And of course, that would be positive or negative, but we're only looking for the length, right? So length is always going to be positive. So we're just going to take the positive root of a squared plus b squared. Okay, so that's how we're going to find our modulus, or the length of that line or that vector going up to our complex number. Okay, so that's our modulus, square root of a squared plus b squared. Okay, now how are we going to find the argument, right? Well, we're going to use our trig to help us find that argument, right? Because we know what b is and we know what a is, so we can use tangent, right? Because tangent, right, is going to be b over a. So we can just use our inverse trig, right? And our argument is going to be the inverse tangent of b over a. And that's how we'll find our argument. So there we go, tangent, -1, b over a. And there you go, we have a way of finding our modulus and our argument. Let's do an example and see how does this all work out, okay? So let's say we have our complex number and it's going to be 1 plus I. Okay, so this is an example. Okay, so what does this look like in our coordinate plane? Let's go ahead and just take a look at that. So we know exactly where it is. We know what we're dealing with, right? So this is real. This is imaginary. Okay, and this is a pretty small little number here, right? Because we're at 1 on the real axis. We're at 1 on the imaginary axis. Our vector just kind of goes right there. It's pretty tiny. right? So we need to solve for r and the angle, right? R and the angle. Very small, very small. Okay, so r is going to be the square root of 1 squared plus 1 squared, which is the square root of 2. Okay. And our argument, right, is the inverse tangent of y over x, which is 1 over 1, or the inverse tangent of 1. Okay, what angle in quadrant 1 has a tangent of 1, right? Just 1 pi over 4. Okay, so there we go. We have our argument. We have our modulus. For that number, that complex number in quadrant 1. Okay, let's do another one. Okay, let's do -1 plus the square root of 3i. Okay, it always is a nice idea to give yourself a little drawing, see what you're looking at. You can do a better job than that. Let's see. There we go. Okay, so this one is in a different quadrant than the other ones we've looked at, right? Because on the real axis, we're at -1, and on the imaginary axis, we're at the square root of 3. So we're about right there. Okay, that's z. Okay, all right, so let's start by finding out what our modulus is, our r. Okay, the length of that is going to be -1 squared plus the square root of 3 squared. Okay, that's 1 plus 3 square root of 4, which is 2. Okay, the length of that vector right there is 2. Okay, we're halfway done. Okay, now we need to figure out that angle right there. Okay. So, y over x, right? Our y is the square root of 3. Our x is -1. So we're interested in the angle that has a tangent of negative square root of 3 and is in quadrant 2. Okay, so what angle is in quadrant 2 and has a tangent of negative square root of 3? Okay, it is 2 pi over 3. And that's it. Okay, we figured out our argument and our modulus for that complex number. Not too bad, right? It's doable. Okay, let's do one more. Okay, this one's going to be -4 square root of 3 minus 4i. Okay, maybe you should do this one on your own. See if you get the same answer we get when we do it together. Okay, so take a minute, draw it first, and then calculate both of the answers, and then we'll see if we get the same answer. Okay, pause the video. Now you're pushing play. Let's see what you got. Okay, first I like to draw the problem. All right, so let's give ourselves a little space here. This one's way down in quadrant 3, right? So we're gonna give ourselves lots of room to draw. Okay, our real axis, imaginary axis. Okay, on the imaginary axis, we're down at 4. Okay, on the real axis, we're way down here at 1, 2, 3, 4, 5, 6. We're way down here at -4 times the square root of 3. We're down here by -7. I think we're about right here. Okay, all right. There we go. That's our spot right there. We need to solve for r and our angle. All right, modulus and our argument. Okay, let's start with our modulus. Okay, so the square root of -4 square root of 3 squared plus -4 squared. Okay, so -4 times the square root of 3, right? That is -4 squared, which is 16, times 3. Okay, that's 48. And 4 squared is 16. Okay, that's the square root of 64, which is 8. And again, normally when you take the square root, you have a positive or negative, but in this case, it's a length. So it's just the positive root. Okay, so the length of that modulus is 8. Okay, now we've got to figure out the argument, or the angle. Okay, and it's the inverse tangent of y over x. Okay, so our y is -4. Our x is -4 square root of 3. That simplifies a smidge, right? You can get rid of those 4's, and you get 1 over the square root of 3. Okay. Now, that's not really going to be on your unit circle when you go to look for 1 over the square root of 3, right? To help us a little bit, you would actually do multiply top and bottom by the square root of 3. And that's going to give us the square root of 3 over 3. Now, that's going to be on your unit circle when you go to look, right? So what angle in quadrant 3 has a tangent of the square root of 3 over 3? Okay, that's what's going to be there for you. And what you find is that in quadrant 3, 7 pi over 6 has a tangent of the square root of 3 over 3. Okay, so there you go. That's your answer. That's your argument for that complex number. Okay, well, now that we have these numbers, right, the argument, what do we do with these numbers now that we have them? What are they for, right? What they're actually for is for writing the polar form of these complex numbers. So let's say in example 1, I wanted to write the polar form of that complex number. The way I would do that is I take that r value and plug it in. Actually, why don't I write what the complex form is first? Polar form of a complex number is r cosine plus I sine. Okay, that's polar form of a complex number. That's why we were solving for your argument, right? Your argument and your modulus. Because now that we know the argument and the modulus, we can just plug them into this equation and we'll have the polar form of your complex number. Okay, so if I took example number 1, the first one we did, I can now plug them into that and I'll have the polar form of a complex number. So I started with 1 plus I, then I solved for r and I solved for the angle, and I can plug those in And there you go. There's polar form of a complex number. Okay, in example number 2, right, we were working with -1 plus the square root of 3i. Okay, and we got 2, and our angle was 2 pi over 3. So you just plug those in. There and there, and you're done. Okay, that's the polar form of your complex number. And let's just show what it would be then for example number 3 we did. Right, we were working with -4 square root 3 minus 4i. Okay, right, that's the one we just did right there. Right, we got 8 for r. And our angle is 7 pi over 6. And that's that. Okay, let's do one where we do the whole thing at once. Okay, let's say we have 5 plus 2i. And I want to convert that into polar form of a complex number. Polar form. This is rectangular form. Okay, I don't want rectangular form, I want polar form. Okay, so to do that, I need to solve for r and for the angle. Okay, so the first thing I do is I got to solve for r, right? I got to solve for my modulus first. Okay, so r, or the modulus, is going to be 5 squared plus 2 squared, and then you take the square root of that. Okay, so that's 25 and 4, or the square root of 29. Okay. And let's say we want to round our answer to the nearest tenth. Okay. Let's say our instructions say round it to the nearest tenth. So this would be about 5.4. Okay. Now we've got to solve for our angle. Okay. This is going to be in quadrant 1, right? +5 and +2. Okay. So y is 2, x is 5. Okay, so 2 divided by 5, inverse tangent on your calculator. Okay, because 2/5, you're not going to find that on your unit circle, right? So in this case, you're going to have to use your calculator. Okay, so you do 2 divided by 5, inverse tangent. Okay, and that's going to give you 21.8 degrees. Now we just plug that into the polar form of a complex number. And you get 5, oh, messy 5, 5.4 times cosine 21.8 degrees plus I sine 21.8 degrees. And that is your answer. Okay, so this right here, right, that's rectangular form. And this right here is polar form. Okay, there you go, you're done. Okay, you can do this, not too bad. Okay, everybody, have a great day.